Okay. Hi, everyone. Welcome back to our One Word seminar. Today, we are very happy to have Dr. Mufan here to give a talk on his recent talk. Dr. Mufan is currently a postdoc at Princeton, working with Professor Boris Hanning on deep learning theory. And previously, he received his PhD from Department of Statistical Sciences at Toronto, working with Professor Daniel Roy and Professor Murat Erdoğan. I think now the time is yours, and let's enjoy Mufan's talk.
All right, thank you for the introduction, and thank you everyone for being here. And yeah, I'm happy to share some of my recent work on infinite depth neural networks. So when I say infinite depth, we are talking about scaling limits of neural networks. So before I start the talk, I do want to briefly discuss what I mean by scaling limits. So in particular, in this talk, when I say scaling limits, I'm referring to the number of variables increasing to infinity, whereas the effect of each variable, so this contribution from each source, is also going to zero. So with this double limit happening at the same time, what you end up getting is the effect of these two limits will offset each other so that you get something that is non-trivial and also non-exploding at the same time. So the simplest example of a scaling limit, which is typically not framed this way, is actually the central limit theorem. In this case, you can see the number of the random variables that you're summing is going to infinity, but the size of each single random variable is scaled by square root of n, and therefore decreases to zero. And because of this exact choice of scaling of square root of n, we end up getting that the limit is something that's very well behaved. In fact, we get a standard Gaussian. So why do we care about these kind of scaling limits? In particular, scaling limits can convert a large discrete system into a single continuous object, right? So on the left-hand side, what we have here is the sum of possibly very discrete random variables. It can be a very, very complicated, arbitrarily complicated object. But when this limit is going to infinity compared to when it's finite, it becomes very continuous. In fact, probably the most smooth, nice object we can ever hope for, the standard Gaussian. And as a result, this simplification here can convert intractable problems to tractable and often analytical theories, which we have seen very often in statistics. So beyond the central limit theorem, there's also a few other scaling limits that I also want to briefly mention. And the first one I want to talk about is random walks. And as you take the number of steps to infinity and the size of each step of the random walk going to zero, you get something called the Donsker invariance principle, where the limit converges to a Brownian motion. At the same time, if you have a random matrix and the size of the random matrix goes to infinity and the size of each entry goes to zero, the spectrum of the random matrix typically converges to something nice. In the case of symmetric or Hermitian random matrices, the spectrum converges to the famous semicircle law. You also can get a lot of very interesting results with particles. So if you have n particles that are evolving and with some interaction to each other, and as the number of particles go to infinity and the contribution of each particle goes to zero, you can, instead of viewing these as a n particle system, you can view them as a cloud of a distribution of particles, and you get this mean field limit. So you can view this as really one single cloud of objects instead of a system of n separate objects. So this also leads to a lot of simplifications. So in the rest of this talk, we'll actually see all three of these scaling limits show up in the talk. And in particular, the questions that we want to address here is, well, can scaling limits help us analyze neural networks, right? Because at this point, neural networks still do not have a satisfying theory of statistical learning, right? If it did, I don't think we would be here today thinking about scaling limits of neural networks, right? So the idea here is that if we can leverage the power of scaling limits and leverage the tractability of what we can get in the limit to study neural networks, this can perhaps help us answer a lot of the questions and address some of the mysteries about neural networks and how it works. So to start, I want to just give a very quick overview of neural networks. So typically in neural networks, we have two concepts of size. one is width, which is the number of neurons per layer, and another one is depth, D, which is the number of layers of a neural network. So very often we can think about neural networks as the limit of at least one of these two measures of size, either the depth or the width, go to infinity. In the rest of the talk, you'll see that actually we will consider both going to infinity. But instead of thinking about scaling limits, another equivalent way of thinking about this is actually a finite size neural network can be a discretization of a continuous limit. Right, so this you can think about discretization in many different ways. You can think about this as perhaps like an integral that you discretize in separate parts, or solutions of the differential equations. You take discretized steps to reach an approximate solution. Now, this is completely mathematically equivalent way to think about scaling limits. However, it'll lead us to get a lot more interesting insights. In particular, the immediate insight that we can get is that if we increase the size of neural networks, we get improved performance. And this is a much expected behavior in numerical analysis if you're talking about discretizations, right? So the intuition of discretization fits perfectly with the observations that we have here. But also at the same time, because we have this phenomenon that the performance of neural networks tends to improve as we increase the size, the number of parameters in the neural network, there is a bit of an arms race going on among the industry labs that are trying to improve the scale, the size of their neural networks over time. Now, there's a couple of things to note here. Is that first of all, the computational costs of some of these models are, near astronomical today, whereas any theory can start to make some significant impact into not only just the cost side of things, but also the time consumed in order to train one of these models. And on the bright side is that, well, because the models are so big, it's really calling for an asymptotic theory. If most asymptotic theories don't need a huge size n to be viable, in particular, for example, central limit theorem, 67 times the third absolute moment is enough. So, this is not in, the hundreds of billions of parameters here that we're seeing with neural networks today. So I think there's a real place for asymptotic theories, in particular scaling limits of neural networks, to really understand how these incredibly deep and mysterious objects work. So I'm not the first person to think about scaling limits. The first person was Raffer Neo in 1995. He observed that as you increase the number of neurons per layer while scaling down the effect of each neuron, a two-layer neural network at initialization converges to a Gaussian process. This is in a similar to central limit theorem type scaling. This is why you get a Gaussian type limit. And Gaussians are great because it's very tractable, as we have previously discussed, which is why this limit led to a flurry of papers to follow up on this work. And I'll just raise a few examples here, generalizing this to deeper networks and generalizing to different architectures, training dynamics, as well as generalization on unseen data points, which is really a fairly complete theory of this limiting regime. The only problem is that, well, this limit is unfortunately not a great model of neural networks. And there's many different ways that it's not a great model, but the most important part, in my opinion, is that it really does not learn features. So this is where the second last layer of a neural network is improved, or in a way, like you can imagine neural network training as engineering these features to help regression or classification. So in this plot, so this is from a paper by Greg Yang and Edward Hu on feature learning, and they showed that in the infinite width limit of a neural network, this is why it's a NTK or neural tangent kernel, the features here between word embeddings are not in a very easily separable kind of state. This is a two-dimensional PCA projection of the embeddings, but you can see that with this limit, you don't get any benefits from training it. However, if you just take a finite width neural network, with 64, which is relatively small by today's standards, you get a very good linear separations, even just by the first two principal component. So what this tells us is that clearly there's something important about finite size neural networks that this limit is not capturing, right? So this is definitely not an appropriate limit to be studying if we really want to understand how neural networks work, in particular about how these features are evolving and helping us in the downstream tasks like regression or classification. So as an alternative, there are many alternatives. I propose to study what's called the proportional infinite depth and width limit. So in this limit, we're not only just looking at width going to infinity, but the depth d also goes to infinity. And in particular, we're going to maintain a ratio of the depth to width ratio is going to some positive constant. So this line of work was first started by Hani and Nika for a single data point, because this turns out to be a fairly challenging regime to study. First of all, they showed that the limit is not Gaussian, which is really great. Well, it's not the same, it's clearly not in the same regime as what Radford-Neo found in the Gaussian process limit. And at the same time, the limiting regime emits feature limit. Now, this is great news, right? This is where I saw this work and I thought, well, this limit deserves some more attention, deserves some more playing around. And very immediately after, I found out that it's actually also a great model of finite size neural networks. So what I'm plotting here is the log output norm of a neural network and initialization, right? So in the gray histogram here is the density, is like the histogram. So if we're going to initialize the neural network 30,000 times, and then plot the frequency histogram with the output in the gray histogram here. This is a finite size neural network. And in the green curve here, we're plotting the prediction by the infinite width limit of the neural network. So this is the Gaussian process limit. And in the red curve here is plotting what the proportional infinite depth of width limit of the network is, right? So this, what we're doing here is we're maintaining the depth to width ratio of 0.1 and taking width and depth to infinity and comparing that against a width 100 and depth 10 neural network, say, for example. And it turns out that you can see that the infinite depth of width limit is great prediction for the behavior of finite size neural networks. Whereas the Gaussian process prediction here in the infinite width limit is only good when the depth to width ratio is very, very small. So when the neural network is proportionally very wide compared to the depth. So this is great news, right? We have found a promising limiting regime with desirable properties, for example, feature learning, and an accurate model of finite size neural networks. So, well, we would like to continue this line of work, and one of the main difficulties is that it's just technically challenging, right? So existing techniques are, either combinatorial or transform based, and you can write a very long, difficult proof to get to this limiting result for a single data point, and even then, it's very difficult to extend beyond that, right? It's just because the techniques are not friendly to work with to begin with. So but even beyond that, I think even more importantly is that neither of these approaches really reveal any key structures about neural networks. Right? It's one thing to write down a proof and write down the results. It's another thing to really understand what is happening within neural networks that can help us understand how things work, and we can take these insights towards some applications. Right? So this is the key distinction from my approach with the previous work, because we have tried to identify a key structure, and I'll explain what this means on the next slide, of the depthwise stochastic process. And we have demonstrated not only we have from the structure, as soon as we put the neural network in this framework, we understand that existing standard neural networks actually suffer from numerical degeneracy. It's numerically unstable at large depths. Right? As soon as you put in this, and we'll see this right away. And then we have, so before we can study a limit, we actually have to prescribe a fix, a modification to sort of standard neural network architectures, and then can we characterize what the stable scaling limit looks like. So let's jump into the math a little bit. So this is what the simplest, I guess, non-trivial model. We'll look at a few other, we'll look at something else in a second, but the overall framework can be generalized to basically any architecture you would like. But in the multi-layer perceptron case, it's the simplest model you can get. We're going to consider just a nonlinear activation function multiplied by a random matrix with the appropriate scaling, so that the variance from layer to layer is not blowing up, and we're going to consider IID Gaussian weights. And the key observation here, this is a structure that we're going to try to identify by looking at this, is that at initialization, if you condition on the previous layer, right, so current layer conditioning on the previous layer, you get IID Gaussian neurons with some covariance structure. So let's talk about this a little bit, because if you condition on the previous layer here, right, condition on the phi of ZL here, right, what you get is a random matrix multiplying by effectively a deterministic vector. So of course you would expect the outcome to be IID Gaussian because the entries of the weight matrix are IID Gaussian. Right? So where does the covariance structure come from? The covariance structure comes from the fact that with different inputs, right? So our input data points X alpha, right? So we're Z superscript alpha corresponding to the alpha input of data points. They all share the same weight matrix. There's only one set of weight matrix for all the different input data points. So if you use the same Gaussian random matrix to multiply by two different vectors, the resulting product are going to be correlated, and they're going to have a very specific covariance structure. So what does this look like in math? Well, you can condition on the previous layers. In fact, we're going to actually condition on all of the previous layers. You'll see exactly why we're doing this in a second. Well, and then you notice that the next layers are IID Gaussians because we have this Kronecker product with the identity matrix. But what is the covariance here? The covariance is exactly the inner product of the vectors that you're multiplying. So this is actually a fundamental fact of Gaussian matrix versus a multiplying by deterministic vectors. So we don't actually need all the information from the previous layers. We only ever need the product, right? This previous layer can be arbitrarily wide, infinitely wide if you care. But at the end of the day, the information that we needed was only n by m, the number of data points by the number of data points, because that's all the covariance information that we needed. So if we were to look at the next layer's covariance matrix, right? So we're going to call this matrix V out here. Notice that if you do the same conditioning, right? Conditioning on all of the previous layers information, we only needed to, in fact, condition on the previous layer's covariance matrix. So some of you probably already recognize what the structure here this is because it is a Markov chain. This is exactly the definition of a Markov chain. If you condition on all the possible randomness informations up to your Lth time, and it's equivalent to just conditioning on the previous step. This is the definition of a Markov chain. And in particular, the index of the Markov chain is the layer index, which is why we call this the depthwise Markov chain. And this is great because, well, we know a lot about Markov chains. We have a rich literature and a lot of tools. And in particular, this is a what's called what you think is a time homogeneous Markov chain. So you would expect this to converge relatively quickly. And we can take a look at, well, if it's Markov chain and converges, what does it converge to? And this is the interesting part because it actually converges very quickly to a fixed point. What I mean by fixed point is that if you were to look at the correlation, so covariance divided by the standard deviations, the correlation converges to 1, or here I plotted the 1 minus the correlation, it converges to 0 fairly quickly. So how can we interpret this is if you have two input data points that have a very large angle between them, and you look at the angle of the hidden layers corresponding to these two inputs across the layers, right? So as you progress over the layers, these angle between these hidden layers are going to shrink to 0. And this is just for neural networks at initialization already. We haven't even trained anything. So this is perhaps, first of all, surprising. And second of all, I think uninteresting in the limit, right? Because if you take depth to infinity, we're just going to map all the input data points to the same output. It's a random direction, but it's going to be the same direction. So this is a very uninteresting limit, from a theorist's point of view. But even more importantly, actually in practice, it's actually going to lead to vanishing gradients. So I'm going to return to this plot later on, but what I'm just going to give you a sneak peek is that this is a weight matrix inside a transformer at initialization. And the gradient with respect to the weight matrices inside the attention block are actually going to vanish. And layer norms do not fix this, right? Whether you use pre-layer norm or post-layer norms, do not actually fix this problem. You are still going to get vanishing gradients in transformers. And this is just purely as a function of increasing depth at random initialization. As we know, in practice, well, practitioners, I'm not an expert on this, but what I have learned from practitioners is that there's a lot of heuristics to try to work around this, whether it's normalization methods, whether it's using skip connections, using Atom, and lots of restarts in practice if you run into instability. So it's something that we would like to avoid as much as possible. So what's the first type of study that tried to address this problem? Is from a group at Google, in particular by James Martins and et al. They realized that, well, it turns out the correlations actually is very sensitive to change of activation functions shape. So what they did is they parameterized what the activation function looked like in terms of several parameters, and they can now target an output correlation that is, let's say, far from one, and numerically optimize it so that you get there. And this change has led to stable training dynamics without resorting tricks, even though there's not a very clear pattern observed from what is actually happening here. What I have found is, well, whenever the network became bigger, their optimization tends to find activation functions that are just closer to linear as the network size increases. Right, so notice the color here. I'm putting this back into this scaling limit regime, right? So as the number of layers increases, you have more and more and more activation functions, right? You apply the hidden layers more times, but the effect of each activation function becomes smaller and weaker, right? So what does this look like for the activation function? So for ReLU, for example, what they have found is that the slope of the ReLU, in particular the negative part, is becoming closer and closer to one as you increase the size of the neural network. And if you have a smooth activation functions, what ends up happening is that you kind of zoom in around a point, right? So it becomes also more and more linear as you zoom in around that point. So while this is kind of cool, well, at the same time, well, it still leads us to ask the question, well, what is exactly the rate that give us the scaling limits? Can we understand, well, how is the shape of the activation function dependent on the size of the neural network? And it turns out there's a very natural way to look at this if we return to the Markov chain framework, because it turns out the Markov chain, if you write these factor as if you have the shape factor as dependent on the width, it turns out there is exactly one scaling that leads to a sense of stable Markov chain updates. What do you mean by stable is that it looks exactly like a discretization of a stochastic differential equation. In fact, with the appropriate step size, 1 over width. Right. So let me make a couple of remarks here. So first of all, this is stable because, well, if in the limit you're converging to something smooth, you can take this limit and without worrying about converging to a fixed point, right? This is actually what happens in practice, is that, yes, as you can see, that the SD and the finite size neural networks behavior of what the correlation looks like, first of all, they are very close corresponding to each other. And second of all, it is very far away from the fixed point at 1. The second remark I want to make is that this is actually the same scaling as random walks converging to Brownian motion. In particular, the second part of this, the 1 over square root of width part of this, is you can interpret this as a random walk, actually. Right, so as the number of steps of the random walk go to infinity and the size of each step, right? So the step size becomes smaller, we are converging to something that looks like a Brownian motion. And this is in fact what exactly it looks like with an SD. So what does the theorem say? Is that,
Oh, hi,
well,
Mufan.
if you,
Sorry to interrupt. Just
no,
a
go for it.
clarification question. So on the
Yeah,
previous slide, does the time t on the x-axis represent the network depth?
that's a very good question. I'm just about to address this on the next
Okay,
slide. It's the depth, the time t is the depth to width ratio,
okay,
right? Because if
okay,
you think about this, if you have step size is 1 over width, and you take d steps, right? Your time is is the depth to width ratio.
okay, okay. I will hold on my questions. Thank you.
Okay, yeah. So, uh, so once again, so this theorem, what it looks like is that if you have a relative activation, for example, we also have corresponding results for smooth activations. If you were to modify the slope at a rate of 1 over square root of width, and now what we're going to consider is the depth and width go to infinity, right? And once again, if the ratio converges to time capital T, so this is kind of like a terminal time of the SD. And then we're going to consider the upper triangular entries of the covariance matrix because, well, covariance matrix is symmetric, so we're going to want to consider the unique entries and flatten that to a vector. Right, so now we're going to have a vector Markov chain of the covariance matrix. And this vector Markov chain converges to the solution of the following stochastic differential equation. And well, I'm going to show you what the coefficients of the SD look like. And it's not super helpful to look at it on its own. But after staring at this for a while, we have some interpretations for you, which I think are more important than the formulas here. So the covariance SD has a drift term, B of t. So this is kind of like the deterministic part of the SD, right? So if you throw away everything else, this is an ordinary differential equation. So how do we interpret this? Is that without modifying the shape of the activation function, the covariance matrix takes an update that is a very large step from one layer to the next, right? So you can think about this as VL plus B of VL, roughly, something very big. But if you were to modify the activation function, the update actually becomes infinitesimal with a step size 1 over n. So in some sense, we just divided the large step by a factor of width in some sense, right? So this is really the way to think about this, right? So we are reducing the size of the step so that as we take infinitely many steps, right, we still get a well-behaved limit. Right? So this is a kind of interpretation from the scaling limit once again. So really, we're reducing the effect of the nonlinearity from layer to layer so that we can take infinitely many layers and they add up to something non-trivial. At the same time, the diffusion coefficient is it's a bit more magical in the sense that it actually corresponds to a Riemannian metric. What I mean by that is if you look at the entries of the covariance matrix as sort of a local coordinates, turns out the inverse of the diffusion coefficients is exactly Riemannian metrics. And the reason why this is significant is that it actually corresponds to a notion of Brownian motion on the manifold. In particular, it is a very specific manifold corresponding to an information geometry. And if people are interested, I'd be happy to talk a little bit more about this in the questions. But I'll return to the structure of affine invariant metric later on in this talk. I want to make a couple more remarks about the SD result. First of all, being that we can actually recover the output distribution of the neural network as well, because the output, even a finite size neural network, if you condition on the previous layers, it is still also Gaussian. And the only condition that we need to uncover this distribution is we just need to recover this random covariance matrix VD here. But we can get this covariance matrix from the SDE at the terminal time, which is at time capital T is D over N. And then we can sample a Gaussian condition on this covariance matrix. So this does help us recover the output distribution of the neural network. A second remark I also want to make is that, well, we do need to compare against, well, against finite-sized neural networks to know how good this theory is, right? And well, I forgot to mention, yeah, we can indeed interpret this as the prior functions that neural networks represent. But we can compare this against finite-sized neural networks. So in the gray histograms, once again, I have plotted what the covariance entry, one single covariance entry in the covariance matrix looks like from 30,000 initializations of a random neural network. This is a ReLU neural network. And just plotting it, a frequency of this 30,000 times. And then with the SDE, we can predict what the distribution looks like by also just drawing samples from the SD. So we discretize the SD directly, and then what we plotted here is a kernel density fit of the SD samples. So not only do you see that this is a very good fit for finite-sized neural networks, we can see that the infinite width prediction actually predicts a deterministic covariance. So this is why I plotted this as a vertical dashed green line here. Is you can see that the infinite width theory can only make a point prediction for the covariance structure. Whereas the SDE theory we have here can predict the distribution of the covariance. So this is much more pronounced when we look at the right-hand side plot with correlation, because in correlation, we can see here there's a huge spike of concentration of probability near 1. And in particular, remember, this is the area that we want to avoid, and we want to understand, how can we make sure the neural network avoids having correlations near 1. The infinite width theory actually can never capture this type of concentration behavior, right? So it's not only that infinite width theory is just an approximation, a pointwise approximation. Is really, I think, not capturing qualitative behaviors of finite-sized neural networks. So this is something that we're very happy to see in some of our simulations here. So up to this point, I think I've only talked about multi-layer perceptrons, which is not very satisfying because, well, this is a toy architectures, right? So I do want to talk about any immediate applications here in transformers because, well, really this set of theory that we have produced here can be replicated really on any architecture that you have, and transformers being the most popular ones, being the foundations of large language models. We wanted to look at this, and in particular, they do also suffer from depth degeneracy and vanishing gradients. They're not, any fundamentally different with respect to this Markov chain structure of neural networks and initialization. So we can, in fact, extend the shaping approach to the attention layers, right? And as we can see here that the correlation here among these are different tokens of the same sequence in the transformer. They also converge to 1 very, very quickly, right? So what this means is that if you, for every single sequence that you put into a transformer, like a sentence, all the embedding representations become almost the same at initialization, right? And this is entirely a function of the nonlinear attention layers. And if you were to weaken the attention layers with this shaping approach, you can indeed avoid this type of correlation degeneracy. And most importantly, we can also avoid the vanishing gradients. Right? As you can see here in the red curve here, this is the shaped transformers where the gradients are no longer vanishing, right? In fact, it's staying roughly the same size across all different layers. So this is great news, right? We think that, we can probably train much more stable transformers as a result. And so this is a very nice application that that I think we found right away. At the same time, also there's another application that we have found in hyperparameter tuning. So as many of you might know, that to find the best hyperparameters such as learning rates, you typically need to try a large sweep of different values for this to work. And ideally, you don't want to do this for your larger sizes of neural networks. You want to do this for the smaller sizes. So for large depth neural networks, we can't really do that. We can't take a smaller depth neural network and we want to and search it and find the best hyperparameters and use it on a large network. And you can naively, this just does not really work. And you can see this with the mu-p scaling. So this is the hyperparameter tuning work out of Microsoft Research and OpenAI, where you can see that with some certain scalings with infinite width scaling. So if you change the width of the neural network, the best hyperparameters do tend to stay the same. But it does not stay the same if you're to change the depth of the neural network as well. So which is the different colors of the lines here. So what is the key here? The key here is to also weaken the nonlinearity of the residual networks. In this case, well, if we weaken it specifically with what we call infinitesimal depth scaling, you can line up the best hyperparameters for all different sizes of neural networks, right? So now you can train a depth 3 with 128 neural network and apply it to arbitrary width and depth on this plot. So, we've only experimented up to, depth 30 and width 1000 because, this takes, 10 runs to make this plot. But, you can imagine putting this on as large a residual network as you can. Another application I want to briefly talk about, I think I don't have that much time, but is the spectrum of the covariance matrix. And in fact, before I start, I just want to briefly mention, well, why do we care about the spectrum of the covariance matrix? Is that, well, if you want to do linear regression, for example, in ridge regression, the part that matters is actually the spectrum of the covariance structure, right? So you can see here that the bias variance decomposition has this variance term, and basically it just depends mostly on the spectral distribution of the covariance matrix, which is sigma here. So, well, entirely characterized by the sigma. So, well, we want to say that, well, what can we say about the spectrum of the covariance SDE? Because, well, this has to be the first step that we want to take towards understanding regression error using features of infinite depth neural networks. So it turns out looking at this SD on its own directly is quite challenging. And in fact, even for the most simple case, considering a linear neural network like this itself is already an open problem. And it already has a lot of challenging structures already. So we're going to focus on linear network first. And it turns out that this structure of the alpha invariance metric arising is actually a hint towards at a stronger symmetry in the linear network setting. So in linear neural networks, what we have is for a random flow map of the SD, you can also think of this as one layer of the neural network or multiple layers of the neural network. The covariance evolution is invariant to whether or not you multiply by a matrix, conjugate by matrix before or after. Right, so you can multiply this matrix as long as it's full rank. You can multiply this either before in the earlier layers of neural network, or you can multiply by later layers of the neural network. You get the exact same distributions. So this is actually the fundamental reason why we have alpha invariance metric is really because of the symmetry that leads to this geometric structure. And the nice thing is that, well, first of all, without loss of generality, we can let the initial covariance matrix be just the identity matrix because, well, we can conjugate the initialized conditions back at the final layer if we choose to. And we can also obtain an SD characterization of the eigenvalues. And this is something we call a geometric Dyson-Brownian motion because it looks very similar to something called Dyson-Brownian motion, where, well, the main difference is being that, well, this is the geometric Brownian motion instead of regular Brownian motion. And the drift also depends on the proportion of the eigenvalues. So this result is more remarkable than I think it looks for a couple of reasons. Is that, first of all, I think anybody who has studied Dyson-Brownian motions before in random matrix theory knows that this is incredibly tractable system to study, right? And there's a lot of things that we can look at this. So in particular, for example, like there's absolutely no reasons that each eigenvalues ST, has its own independent Brownian motion. There's no correlation structures. There's no interactions either between the different eigenvalues on the Brownian motion part of this, but all of the interactions come from the drift component, come from the deterministic component. So you can very easily isolate the interaction of the eigenvalues here, right? And you can think about this as kind of like an interacting particle system, again, a scaling limit that I've talked about, which we'll study very immediately after this, because, well, each eigenvalue is kind of like a particle, and they interact with each other through the drift. And then we can consider, well, how can we take the limit as the number of particles go to infinity, which is also as the number of data points go to infinity, and characterize this limit. I think I'll just skip this slide for now. And we do need the time change, which is exactly the same as the Brownian motion scaling, actually. So many of you might know that, multiplying by a factor for Brownian motion is equivalent by scaling the time of this down. So this turns out to be exactly the same scaling we need compared to the classical random matrix theory scaling. And then we're just going to need to maintain a slightly different ratio, which is the depth multiplied by number of data points divided by width is equal to a constant positive time here. And this limit, I think I won't say too much, is that we can characterize this by a fixed point equation. And I'll just show you what the result looks like numerically. And so in the linear network case, the eigenvalue spectral distribution here is plotted in the gray histogram. Now this is a single realization of the linear neural network, right? These are just all the different eigenvalues of one single possible covariance matrix. And then you can solve the fixed point iteration in the red curve here, right? And it's a very good fit, which we have. We also actually have a approximate formula when the time, well, remember it's the depth multiplied by number of samples divided by width ratio is very small. We also have a closed form formula for this. And this blue curve here, it's also pretty good, actually. But most interestingly, it's almost the Marchenko-Pasteur law, which is also a classical spectral distributions that we see from random matrix theory. So I think at this point, I do want to just quickly summarize because I'm running low on time. We studied the proportional infinite depth width limit of neural networks. And by viewing the initialization as a depthwise stochastic process, we can resolve the correlational degeneracy and therefore also vanishing gradients by shaping the nonlinear activation functions. The limit is characterized as a covariance SD. And using this framework, we also have practical applications, so not just theoretical results, on stabilizing transformer gradients, and also talk about hyperparameter tuning as well. And finally, we have also described the limiting spectrum of the covariance SD for linear networks. So the SD can actually yield a lot of significant structure as well from the spectral perspective. So before I wrap this up, I want to just briefly thank all my collaborators that have made this work possible. And at this point, I want to thank you for listening, and I'd be happy to take any questions.
Yes, thank you, Mufan, for this great talk. I think this talk is really great and the work is also very interesting. So let me first stop the recording. I do have my questions, but I can